Hello, I'm Seema and welcome to part 26 of the chapter Thermodynamics. As I promised in part 25, we'll be solving 3 more numerical problems on enthalpy before we proceed to entropy and spontaneity of reactions. This is now question 6.13 of your NCERT textbook exercise. The question reads, given N2 plus 3H2 is 2NH3, all in the gaseous states. Nitrogen is in the gaseous state, hydrogen is in the gaseous state, and the enthalpy of this reaction is minus 92.4 kilojoules per mole. What is the standard enthalpy of formation of ammonia gas? Do you know, first of all, I would suggest whenever you are solving numerical problems and you are asked such a question, whatever has been asked, the definition of that particular thing should always run in your mind. Because if you remember the definition, you can never go wrong with the answer. What is standard enthalpy of formation? Standard enthalpy of formation is the enthalpy change that occurs when 1 mole of a substance is formed from its elements in their standard states. So when you have 1 mole of a substance that is formed and all the reactants and products should be in their standard states. So what would be the standard enthalpy of formation of ammonia? It would be the amount of enthalpy change that takes place when 1 mole of ammonia is formed from its constituent elements. So this was the definition that you know is the definition of standard enthalpy of formation. So if you look at this equation, it is a balanced chemical equation. You have 1 mole of nitrogen combining with 3 moles of hydrogen to give you 2 moles of ammonia. And the aim is to find out to have 1 mole of ammonia. So what should you do? You should divide this equation, the entire equation, by 2. And if you divide the entire equation by 2, you'll get a molar equation, that is for the change for 1 mole or the formation of 1 mole of ammonia. So how would I change it? It would be half of nitrogen gas combines with 3 by 2 moles of hydrogen gas to give me 2 by 2, that is 1 mole of ammonia in a gaseous state, right? And what is the enthalpy? When you divide or multiply an entire equation, you have to multiply or divide the enthalpy to get the answer. So if the enthalpy of reaction here, the enthalpy of reaction is minus 92 would now become half of minus 92.4 kilojoules per mole, right? This enthalpy would become half of this, and half of this would be equal to how much? 90 is 45, 46. 46.2 kilojoules per mole. And since it has a negative sign, the enthalpy of formation. So we'll say the enthalpy of formation, standard enthalpy of formation of ammonia would be equal to minus 46.2 kilojoules per mole. And this will be your answer. Let us now move on to the next question. Now this is question 6.14 of your NCERT textbook exercise. Let us now read the question. You have to calculate the standard enthalpy of formation. Again, it's the same enthalpy, the enthalpy of formation. And it's standard. It means all the reactants and products should be in their standard states. And it is enthalpy of formation. It means you're producing 1 mole of the substance, right? I've reminded you of what standard enthalpy of formation is. So the question is that you have to calculate the standard enthalpy of formation of methanol in the liquid form from the following data. And what's the data that is given to you? You have methanol combining with oxygen to give you carbon dioxide and water. It is actually combustion of methanol that is taking place. And the enthalpy of this reaction is equal to minus 726 kilojoules per mole. Then you have carbon, that is graphite, combining with oxygen to give you carbon dioxide, and the enthalpy of combustion of carbon or graphite is given to you. And you have hydrogen combining with oxygen to produce water, which is actually the burning of hydrogen to produce water. And the enthalpy of formation of water here is said to be minus 286 kilojoules per mole. So what do you observe in these definitions? That all of these reactions are actually combustion reactions. But yet, they are also formation reactions. They are, in these 2 cases, they could be formation reactions. This is combustion, of course, so it has been written combustion also. And this is the enthalpy of a reaction, which is usually a general term that we can use for any kind of reaction. So we see that these terms have only been put in to confuse you a little. Basically, whatever is the nature of the enthalpy change that is taking place, you know this is the enthalpy change that took place in this particular reaction when the equation was balanced according to these numbers. If it is fractional, in the case of enthalpy of formation, you need only 1 mole of the product. Therefore, in order to get only 1 mole of the product, the equations, when they are balanced, they usually are fractions. So anyway, here you see it is 3 by 2 and it's a fractional equation, although it's a molar equation. But here we are using only, even in enthalpy of combustion, if you remember, what is the definition of enthalpy of combustion? It is the amount of heat which is produced by burning 1 mole of a fuel. So if it is enthalpy of combustion, you should be using only 1 mole of the fuel. So here we have 1 mole, therefore you will need only 1.5 mole of oxygen to burn completely 1 mole of methanol. So it's just, you know, the equations, they give you a hint, and the enthalpies that are mentioned, they give you a hint of what is the process and why the equations are fractional. Well, this was just a little knowledge to go along with it, with the numerical problem. Let us now solve the numerical problem. The question is that you have to calculate the enthalpy of formation of methanol. So the first step should be, we should know what is the desired reaction. So the desired reaction is formation of CH3OH, 1 mole, from its constituent elements. And whatever that equation is, it should be the sum total of all of these, because we'll be using Hess's law in the end, right? So we'll say the desired equation is that you have carbon, and you have hydrogen, and you have oxygen in the reactants. I'll put the arrow under the arrow. And the product should be CH3OH, that is methanol, in the liquid state, right? And carbon, hydrogen, and oxygen should be in their gaseous states, and carbon should be a solid, that is in the form of a graphite, So this is and solid or graphite is the same thing. The solid form, we choose the allotropic form, that is graphite. I'm not writing all of it due to lack of space. So now this is our desired equation, but we have to balance it. So you have 1 atom of carbon, 1 atom of carbon. How many atoms of hydrogen? You have 3 plus 1, 4 atoms of hydrogen. But in 1 molecule you have only 2, so we'll have to multiply this by 2. We need 4 atoms of hydrogen and 1 atom of oxygen. Therefore, in 1 molecule there are 2 atoms, so I'll have to divide this by 2. So in other words, this is the equation that I want. Carbon plus 2H2 plus half O2 will give me CH3OH. And this is the equation that I should get as a sum of whatever information has been given to me. And in order to do that, I might have to flip the equations, I might have to multiply certain equations by certain numbers and come to arrive at this result. So that then whatever change occurs in their enthalpies, I can use Hess's law and find out the sum of all those steps in order to come to my final step. So this is how we theoretically find out the enthalpies of certain reactions, of rather all the reactions. So now what is it that we have here? In the reactants, we have carbon in the reactants, we need hydrogen in the reactants, we have hydrogen in the reactants, and we need oxygen in the reactants, we have oxygen in the reactants. We need methanol in the product. There is only 1 product that we need, that is methanol. And where do we have methanol here? We have methanol in the first reaction, and that too in the reactants. So what should our first step be? Our first step should be to have the reactants on the reactant side and the products on the product side. So I will flip this first equation. We'll have to flip this equation. If we flip it, we turn it completely. So we have carbon dioxide. Now when you flip it, I left space here for it. You get carbon dioxide gas plus 2H2O liquid will be giving you CH3OH in the liquid state plus 3 by 2 oxygen molecules in the gaseous form, right? And when you flip the entire equation, the enthalpy, the sign of the enthalpy, the magnitude remains the same, but the sign changes. So the minus becomes a plus 726 kilojoules per mole, right? So now we have this equation has been changed So we are now left with these three equations that we have to sum up. This equation has been changed, so we are not using this. We are using these three enthalpies because these three are going to bring us to this equation. But we have to have the same number of atoms of each element on each side. So in order to do that, let us first find out, do we have the appropriate number of atoms of each element on each side? The first thing that I notice here is that carbon, you need only one, you have only one. 2 moles of hydrogen makes it 4 atoms of hydrogen. But here in the reactants, take a look, how many hydrogens you have? You have hydrogen here, which is 2 atoms of hydrogen, but of course in the form of water. Look here, the water is, okay, let us do one thing. Let us first cancel out whatever is there in order to see what we are left with. We need 2 moles of hydrogen atoms, that is 4 atoms of hydrogen. And the water molecules that are formed here, if I multiply this by 2, then the oxygen also gets multiplied by 2 and this becomes equal to 1 because 2 by 2 is 1. And you multiply this by 2, therefore you'll have to multiply the enthalpy by 2 too. Now you have 2 moles of hydrogen that you wanted and how many? 1 mole of carbon, and we need half a mole of oxygen. There's oxygen scattered all over, so we'll come to oxygen later. We need 1 mole of methanol. We have 1 mole of methanol, which means we don't have to multiply this equation by anything. So now we have the things to be cancelled. We've got the numbers here. Let us see what is going to get cancelled out. The carbon dioxide, which is produced on this side, is used up here, right? 2 moles of water which are produced here are used up here. So what we needed graphite, we've got it. We needed 2H2, we've got it. We needed methanol, we've got this. So these are the things that we don't really need to touch because these are the things that were required in our final equation. So now we are left with oxygen, balancing of oxygen. These are 2 moles of oxygen if you really look at it. And what do we need? We need only half a mole of oxygen. And in the products we have 3 by 2 moles of oxygen. 3 by 2 is 1.5 moles. So 1.5 moles of oxygen is produced while 2 moles of oxygen is there in the reactants. So how many moles of oxygen will be left in the reactants if we cancel out the oxygens? If we cancel out the oxygens, we'll be left with half a mole of oxygen. So half a mole of oxygen will be left in this reaction. Because again, I would repeat, 1.5 moles of oxygen is there in the products, while there are 2 moles of oxygen in the reactant side. So 2 minus 1.5 leaves you with 0.5, that is half a mole of oxygen here. So this equation is, we have arrived, the sum of all these 3 equations is definitely this 3rd equation, this 4th equation. So now the sum of all these enthalpies according to Hess's law should be the enthalpy of this particular change. And that is what we want. We want the standard enthalpy of formation of methanol. So the standard enthalpy of formation of methanol, CH3OH, would be equal to the sum of all these. That is minus 393 kilojoules per mole. Or let me write the units in the end. Minus 393 plus you have minus 286 kilojoules plus 726 kilojoules per mole. Right? So when you solve this, you have 2 negative values and 1 positive value. When you solve this, you arrive at the answer minus 239 kilojoules per mole. Minus 239 kilojoules per mole. So this was your solution to question number 14. Now before I wind up this video, I'm going to do one more numerical problem. So let us now come to question 15. The question reads that you have to calculate the enthalpy change for the process. CCl4 gas gives you carbon gas and 4 chlorine atoms in the gaseous state. You have to find out the enthalpy for this particular reaction. And then later it says that you have to calculate the bond enthalpy of CCl bond in CCl4. You have to tell what is the enthalpy, the bond enthalpy of carbon and chlorine in CCl4 molecule. So this is the second part of the question. Let us first deal with the first part. There's a certain data, certain information that is given to us. What is this information? The enthalpy of vaporization of CCl4 is given. The enthalpy of formation of CCl4 is given. The enthalpy of atomization of carbon is given to us. And fourth is the enthalpy of atomization of chlorine that is given to us. So let us first elaborate this data that is given to us in the form of equations. And then we know what is the final equation that we have to arrive at. And then how can we twist or change these equations to get this result, and finally using Hess's law find out the answer, as we did in the previous question. So let us write these in the form of equations. Enthalpy of vaporization of carbon tetrachloride. So you have CCl4 and it is in the liquid state and it is vaporizing. What is vaporization? When a liquid turns into a gas. That process is known as vaporization. So CCl4 turns into CCl4 gas from the liquid to the gaseous state, and the enthalpy of this reaction is 30.5 kilojoules per mole. 30.5 kilojoules per mole is the energy here. Okay? In the next reaction, what do we have? We have enthalpy of formation of carbon tetrachloride. What is enthalpy of formation? The enthalpy change that takes place in the formation of 1 mole, the standard enthalpy of formation, 1 mole of a substance from its constituent elements in their standard states. So we know we need to form 1 mole of carbon tetrachloride here. I should have written this a little away because I would like to write all reactants and all products together. So we started with CCl4 liquid and resulted in the formation of CCl4 gas. Right? Here we have C carbon, which is in the form of graphite, combines with chlorine, 2 molecules of chlorine in the gaseous state to give you 1 mole of CCl4 in the liquid state. Right? So these are all in their standard states now, and the enthalpy of this reaction is minus 135.5 kilojoules per mole. Right? Delta H, irrespective of what kind of enthalpy it is. Now, what is the enthalpy of atomization of carbon? We know carbon is present as graphite in nature. So carbon solid will turn into carbon, solid is in the form of graphite, it turns into carbon that is gas. Now, the atoms are not combined together, they are separated, and therefore this would be the enthalpy change in this reaction would be known as the enthalpy of atomization. So, enthalpy of the change of this reaction is 715 kilojoules per mole. Right? Now, the next change is the enthalpy of atomization of chlorine. We know that chlorine is a molecule, a diatomic molecule in the gaseous state, and we need to break the bonds of 1 mole of chlorine to get 2 moles of chlorine atoms. And this reaction would give you the enthalpy of atomization of chlorine, which is given to us as 242 kilojoules per mole. Right? Now, what is our desired reaction? The desired reaction is given to us in the beginning. So we'll write down the desired reaction here. The desired reaction is that you should have CCl4 in the gaseous state, in the reactants, and in the products, what should you have? You should have carbon in the gaseous state, and you should have 4 chlorine atoms, right? And the enthalpy of this reaction is to be found. That is your question. How do we arrive at this using this information? What do we want? We want carbon tetrachloride gas in the reactants. We want carbon tetrachloride to be in the gaseous form in the reactants, but in these equations we have carbon tetrachloride in the liquid state in the reactants. We want the gaseous one. So what should our first step should be? Our first step should be to flip this reaction. So we will flip this reaction. Flipping the reaction is nothing but subtracting the reaction when we are using Hess's law. But here, let me flip it. When I flip it and I write down this equation, I'll get CCl4 gas giving me CCl4 liquid. And when I flip the reaction, the enthalpy, the sign of the enthalpy changes. It becomes minus 30.5 kilojoules per mole, right? So I have now got CCl4 gas in the reactants, which was my intention. The next thing is that I should get carbon in the products, and the carbon should be in the gaseous form. I do have carbon in the gaseous form in the product, so for the time being, I don't need to do anything. And then I have 4 chlorine atoms in the product. 4 chlorine atoms, and we have only 2 chlorine atoms here. So what should we do? We should multiply this reaction by 2. If we multiply this by 2, we'll get 2Cl2 here, and the 2Cl multiplied by 2 would become 4Cl here, and this will have to be multiplied by 2, and this will come out to be equal to 482 kilojoules per mole. Am I right? So what have I done in this step? I have turned the 4Cl, I've got 4Cl here. I got CCl4 in the gaseous state here. Now what else? I got carbon in the gaseous state here. So if you really look at it, I do have these things in the proper place. But yet, this reaction, the sum of all of these should be this reaction. Is the sum of all these steps coming out to be this reaction? Now, we'll ignore the first reaction because we flipped it and I wrote it here. So we're using 4 equations. We have carbon graphite in the solid state. And do we need carbon graphite in the solid state and carbon here in the solid state too? And the reactants do not have carbon in the solid state. And if you really look here, we have carbon tetrachloride in the liquid state in the products here in this step and in this step. But we do not need carbon tetrachloride in the liquid state here. But what have we done? How did we get? We got this step. We flipped this reaction in order to get carbon tetrachloride in the gaseous state on the reactant side. And we got carbon tetrachloride in the liquid state in the product side. Now we should have carbon tetrachloride on the reactant side somewhere to cancel it out, because we do not want carbon tetrachloride in the liquid state on either side of the equation. Neither is it present in the reactants, nor is it present in the products. So if it is appearing in these reactions, it should appear twice, once on the reactant side and once on the product side, so that it gets cancelled out. So what do? The second reaction, see, if we flip it, it solves all our problems. If I flip the second reaction, what do I get? I get CCl4 in the liquid state. That is what I wanted, because I had CCl4 in the products in the liquid state and I need something to cancel it out with. So I flip the second reaction. CCl4 I get, and I get carbon in the solid state, the graphite I've written as solid, plus 2Cl2 in the gaseous state. And since I flipped this, the enthalpy change, the sign would change. The second reaction, so this becomes equal to plus 135.5 kilojoules per mole. Do you see this? So when you flip a reaction, the enthalpy change, the sign of the enthalpy change also changes. Now I am using these 4 reactions because these 2 I flipped and I rewrote them. So this is the form in which I want my equations. Let us see let us start cancelling out things and see, do we arrive at what we wanted now? Carbon solid that is present here. Do we want carbon solid here? No. So carbon solid should be there somewhere in the products. It's here. So it gets cancelled out. Carbon in the gaseous state, yes, we do want it and we do have it here. So this is desired, right? Chlorine molecules, do we have them here? No. They should be cancelled out. So 2Cl2, look here, 2Cl2 gets cancelled out. CCl4 gas is what we want. Yes. So this is desired. I'll circle the desired parts. This is desired. CCl4 in the liquid state. In the liquid state is what we do not want. So these 2 get cancelled. The 4Cl in the products, desired. We want it. So we get carbon, 4-chlorine in the products, and we get CCl4 in the gaseous state in the reactants. Do you see? Which means that we have now summed up these equations correctly. So if we have done that and we took care of the signs and we multiplied whatever we did, we carried out the changes in enthalpies also. Now all we have to do according to Hess's law is find the sum of all these enthalpies to get the enthalpy of this reaction. So the sum of all enthalpies, delta H for this reaction would be equal to 715 kilojoules per mole plus 2 into 242 is 482 kilojoules per mole plus minus 30.5 kilojoules per mole plus 135.5 kilojoules per mole, right? And when we find out the sum, when we solve this, what is the answer that we arrive at? It is 1304 kilojoules per mole would be our answer, right? This is the answer that you get. And what is the next part of the question? So this is the enthalpy of this reaction. You calculated the enthalpy change for this process. And the second part of the question said that you have to calculate the bond enthalpy of CCl bond in CCl4. We know that even if you have identical bonds, now in CCl4 there will be 4 carbon-chlorine bonds and it will have a tetrahedral structure, just like you have it in methane, right? And these 4 bonds are identical. And the bond enthalpies of each of the bonds should be the same. When you break a bond, one bond, whatever the enthalpies, the second bond, third bond, fourth bond, they should have the same enthalpies. But we know that successive enthalpies of bonds, even if they are in the same molecule and they are identical, is not the same. So when he asks you for the bond enthalpy of CCl based on whatever data we have, we cannot give you the enthalpies of each bond. We can talk of the average bond enthalpy. So what is the average enthalpy? Whatever is the total enthalpy of breaking all of these bonds, we will divide that total sum by 4. So the total enthalpy of this reaction, that is breaking up of the bonds of carbon and chlorine, do you see you're getting everything in the atomic form? So whatever is this enthalpy of reaction will give is actually the enthalpy of atomization, breaking up of bonds, or bond enthalpy in the case of CCl4, 1 mole of CCl4. So for one bond, if this is the enthalpy for 4 bonds, then the enthalpy for one bond would be you use unitary method, divided by 4, and therefore bond enthalpy for CCl bond would be equal to 1304 divided by 4. And what does this come out to be equal to? It is 326 kilojoules. 326 kilojoules per mole. Remember, in thermodynamics, whatever enthalpies we are reporting are for moles. They are not for single atoms. They are not for single molecules. We always assume them to be for a mole of a substance. So you have 1 mole of carbon tetrachloride molecules and which have 4 moles of CCl bonds. Out of these 1 mole of the bonds, the average enthalpy would be 326 kilojoules per mole. So these were numerical problems on enthalpy. And this is the end of this video. In the next video, I'll be telling you about entropy. So if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.